Hello, Tanya Laird here, and welcome to part 3 of lecture 10 of ENGR 231 Engineering Statics. In this portion of the lecture, I want to work through some examples of applying the method of sections to trusses. So I'm just going to work through a couple examples here and consider trusses the method of sections. And so we're going to use the steps that were outlined in the previous video. The main steps, again, we're going to first find any external forces that we can, or find any external reaction forces that we can. 2, we're going to determine which member forces we want. Usually in terms of academic problems, these are going to be given. Third, I should say, we're going to carefully choose a section that we wish to cut, and then we're going to isolate the section and then apply static equilibrium to solve for whatever internal forces we are looking for. So I'm just going to work through 2 examples, one a simply supported truss, and the other actually kind of interesting, a statically indeterminate truss. So let's work through something like this here. And I suppose I can do this one in English units. Now I'm going to draw a truss that is decently sized with a whole bunch of bays in it. Like so. And then maybe one more member like that. Okay, so I think I'm going to go ahead and give these some joint names. A, B, O, C, D, E, F, and G. And then the bottom chord I'll have H, I, J, K, L, M, N, O, P. And now I know my ABCs. Okay, I'll put a pin joint there and a roller support there, or a pin support there and a roller support there. So this will be a nice simply supported truss. And let's say this thing has on joint E a load of, perhaps 15 kips. And then I'll give this some dimensions. So let's say this is, maybe 9 feet tall. And then maybe, let's see, maybe each of these is, let's go 12 feet wide. And I'll just say that's typical. So each of these bays, each of these bays here is 12 feet across. And we have 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay. So all this is given. And I want to find, let's find the force in member LM. In member LM. And maybe also, let's also do EL. In members LM and EL. And so I'm just going to go ahead and star those, or highlight those, and maybe orange or something. LM and EL. So I'm looking for those members here. Now, if we looked at the list of steps number 4, the first step I usually try to do is apply static equilibrium to the entire truss to see if I can solve for the external reaction forces. And by doing that, or in doing that, I'm going to treat the truss as the entire truss as a single rigid body. So let's go ahead and do that. And the first step will be to solve for external reaction forces. For our external reactions. So I'm going to treat the entire truss as a single rigid body. And what I mean by that, of course, is that I'm not concerned with the internal member forces. So because of that, I am only just going to draw the truss as just a very basic block object, just like a great big trapezoid. Because again, when I'm looking at the external reactions, I'm treating the entire truss as just a single big object and saying, okay, well, if this entire object, ignoring everything that's going on inside the object itself, all those internal forces, what kind of forces are needed to keep this thing in place? So let's look at the reactions. We're going to have an HY and an HX. an HY, and an HX, because this is a pin support. Then on joint R, we're going to have an RY. And then applied here at joint E, we'll have a 15 kip force downward. Now I want to go ahead and put in place the dimensions, or the relevant dimensions here. So let's see, this is going to be from R to M, or this to member EM, I should say, is going to be a total length of what? Well, we have, let's see, 12 times 3, so that's going to be 36 feet. And then 1, 2, 3, 4, 5 bays, so that's going to be another 60 feet. 12 times 5 is 60, of course. So another 60 feet there. And then we're going to have a height of 9 feet. So I think I'm going to get these forces by just doing balance of moments. Well, the first thing I can do is knock out the HX by doing a summation of forces in the X direction. And that's just going to be HX and nothing else. So that clearly leads to the knowledge that HX is equal to 0. There are no horizontal loads applied to the truss, so even though this thing does have the capability of resisting lateral loads, it's not going to experience any, so therefore HX is 0. Next, I want to do a summation of moments about point H, and that's going to allow me to get RY here. Summation of moments about point H, and so I'm going to have the 15 kip force, and that will be a negative out of the moment from the negative 15, or from the 15 kip force, and that will be a negative moment because it is clockwise rotation about point H. So we'll have negative 15 kips times a moment arm length of 60 feet, and then I'll have a positive moment from RY, again because that will be counterclockwise rotation about point H, and a moment arm length of 96 feet. And all of this is equal to 0. Then RY is going to be equal to 15 times 60 feet, or 15 kips times 60 feet divided by 96 feet. And I probably could simplify that fraction into an exact form, but I think I'm just going to do this as an ugly decimal for now. 15 times 60 divided by 96, and that comes to 9.375 kips. And so actually not such an ugly decimal, that'd be some 8s there. Okay, next I want to do a summation of moments about joint R here, and that will allow us to get HY, the last reaction force. Let's do a summation of moments about joint R, and this is going to be very similar. HX, just like last time, is not going to generate any moment about point H because its line of action passes through point H. And so then, as I do a summation of moments about joint R, I will have HY, and HY will produce a negative moment because clockwise rotation. So that will be HY times a moment arm length of 96 feet, just like last time. But this is going to be negative here. Then the 15 kip force will be producing a positive moment about joint R. So plus 15 kips times a moment arm length of 36 feet. And this is going to equal 0. And therefore HY will equal 15 kips times 36 feet divided by 96 feet. So 15 times 36 divided by 96. And this will be 5.625 feet, or sorry, 5.625 kips, not 5.625 feet. Okay, and if we do a quick balance of forces in the vertical direction, we can see that 9.375 plus 5.625 is in fact equal to 15, and so we can see via a summation of forces in the vertical direction that we have produced the correct forces. So now we do know our reaction forces. So step 2 is going to be to determine a section. We'll figure out what member forces we want, so we got that part taken care of. That was just given to us. Part 3, or step 3, will be to select a cut section. And this is often the hardest part of this process. So let's consider this. Now, if you remember our previous discussions in part 1 of this, or part 2 of this lecture, we looked at some of the limitations in, or some of the considerations when designing a cut section or choosing a cut section. First of all, we need to make sure we actually have the members that we want. So I need this cut. I need to cut across this member and this member. I also know I can't cut across any joint because that's kind of cheating. That doesn't really work very well. It doesn't work with how we model our joints and members. So we can't cut across a joint. So we can only cut across members. So what could we do? Well, we could do something like this here, and that's probably the easiest and most obvious way. And that's probably what we're going to end up doing. Or we could also do something really weird. We could do something like this here, but that produces an immediate problem. So one problem this produces, well, there's a couple problems. First of all, one problem is going to be that if we look at this, one of the major problems with this is that we're going to have 1, 2, 3, 4, 5 cuts across members. And as we recall from previously, every time we cut across a member, that is another unknown force. And if we're going to be analyzing equilibrium about an object, we want to make sure that we're only dealing with up to 3 unknowns. And so really for this particular problem, I have only one choice in my possible or practical cuts. Now we could do different cuts, and we could do this cut, but then we'd have to do another cut to make sure we had the right number of unknowns, and it would just be a pain in the butt and really defeat the entire point of the method of sections. So instead, I'm going to cut right down the middle here. And every time I cut across a member, that's going to reveal another internal member force. And so after that, my choice is then whether I just want to move, whether I want to analyze this section, or whether I want to analyze this section. And either is arbitrary, either is an option. Or I shouldn't say either is arbitrary, the choice is arbitrary. Either is perfectly fine. Now, personally, when I have a truss like this with just a single load applied to top of it, I often like to just go with the portion without the load on it, because then I don't have to worry about the balance of moments for that particular force here. I think so because of that, again, we could do this with either one, but I think I'm going to use the section on the left. So we have our section chosen. And next, in step 4, I'm going to go and draw that section out and start applying static equilibrium. All right, so now for part 4, we're going to go and apply static equilibrium to the section we already described. So I'm going to draw out this section here, and I'm just going to draw this out as a trapezoid, not bothering to really draw all the internal members, because again, we're treating this entire thing as a single section, a single rigid body, and all we're concerned with is the forces in the members that we have cut across. So I'm not concerned with the member forces and say like or the forces in members say AB, BC, CD, etc. I'm only concerned with the forces in the members that my cut is going across. So I'll have to go back and forth a bit here to get this. Let's get that. Now let's see. So we're going to have our trapezoidal arrangement here. I'll just draw it out like this. And again, I'm just ignoring all of the member forces, or the forces of any member that is inside this section. So then let's go ahead and I do like to label the critical joints, or at least the ones that define the shape that I'm cutting out. So I'll use A, D, L, and H for starters. A, D, and then L and H there. Then I need to show all of the forces that are present on this section. And the first force is going to be HY. I could draw HX, but it's actually 0, so I can just ignore that for now. So we have HY. Then I'm going to have the 3 cut member forces. I'm going to have an FDE, an FLE, and an FLM. FDE, then an FEL, and then an FLM. FLM here. Now I should indicate the slope angle on this. This is a 3, 4, 5 triangle. If I divide both these by 3, I can see that this is a 3. All of these slopes are 3, 4, 5, with the 3 on the vertical rather than the horizontal. So this is a 3, 4, and 5, like so. Then I should also indicate critical points. I like to do this because I often like to find critical, or just define any joints that are that forces are going to. So this is joint E here, And this is joint, I guess that's joint M here. Actually, let me remove that and get that in line there. So this would be joint M, and then relabeling that force, we would have FLM. And that's it. Oh, of course, HY, we should put the value on it. HY is 5.625 kips. HY is 5.625 kips. And I should indicate important dimensions. So let's see, each of these bays is 12 feet across, and along here we have 3 of them, well, not including the diagonal, which makes 4. So this is 36 feet along AD. It's 48 feet from H to L. From H to L is 48 feet, and the thing is 9 feet tall. And the overall truss is 9 feet high, like so. And then this will be 12 feet from here to here as well. So just repeating some of the dimensions from the previous slide, or from the previous canvas. Now, let's see. So how can we work through this? Well, first of all, you might ask, and it's a very common question to ask for us, or a very common question asked by static students, is they'll see this 15 kip force, then they'll ask themselves, wait, why isn't this appearing on my cut section? So we have we do not have the 15 kip force listed on here. Don't we have to include that somehow? And there's a part that rationally that kind of makes sense. Like, shouldn't we have to include all of the forces that are applied to the truss? And the truth is we do include it. It's just not included explicitly. So when we separate out this section, the effect of that 15 kip force doesn't disappear. Rather, it's baked into this 5.625 kip force here. And so it's hanging out over here somewhere. Well, actually, it's on joint E, but we're not including joint E in our analysis. I'm going to just use that for like summing moments or something like that. Okay, so that force is still affecting this section, but it's only affecting it in the terms of its reaction, its effect on the reaction here. And so, again, what we have fundamentally done is we have cut out, we have, in our analysis, we have imagined cutting this section of the truss out, and then said, okay, those members that were previously holding the truss up at the middle there, if those are no longer present, what kind of forces must be put in place via my little force magic wand that I discussed in the previous lecture to hold this thing in place? Okay, so we have this, our free body diagram drawn out. Now let's just go ahead and work through the equations of equilibrium. So I have a couple of different ways I could do this. I think the first thing I'm going to do is, the easiest way to get FEL would be to do a summation of forces in the vertical direction. So let's do a summation of forces in the vertical direction. And the reason I want to do that is because with the exception of the reaction force HY, I have no other vertical forces on this except this internal member force, the force in member EL. Also, important to note, you will note that I drew all of these assuming tension. I drew them the exact same way I did in the method of joints when we were looking at that in lecture 9. And so I initially just assumed everything is in tension. I assumed effectively I assumed all the forces would be positive. And then if I get a negative number for one of the forces, I know that force will be in compression rather than in tension. And of course, this is just for trusses. Later when we get to frames, things will be a little bit more complex. Okay, so I'm going to do a sum of forces in the y direction. I will have FEL times, I'll use the slope ratios to get its component, 3/5, then plus 5.625 kips, and then this equals 0. Then if I solve for FEL, the force in member EL, I get negative 5.625. And then I'll multiply by 5/3 in order to get that. Okay, so let's go ahead and multiply that out. Negative 5.625 times 5/3. And this comes to negative 9.375 kips. Negative 9.375 kips. And of course, this will be in compression. So we have FEL, and what we were asked to find is LM and EL. So we now have one of our desired forces. Next, though, I think I want to get the force in member LM. Now, I could try to do a summation of forces in the horizontal direction, but each of these three forces is going to have, or each of these three members is going to have a horizontal component to their force. So that's probably not the best thing to do. Instead, if I just want to jump directly to the force in member LM, the most efficient way to do that is going to be to take a summation of moments about joint E. A summation of moments about joint E. And the reason for doing that is fairly simple. If you look at this, we can see that FEL and FDE both have lines of action that pass right through point E. So therefore, they will not generate any moment about that point. As we discussed previously in balance of moments, if something is going to be in equilibrium, it's going to be in equilibrium about a couple things. First, it must be in translational equilibrium about any set of axes. Second, it needs to be in rotational equilibrium about any given point. So I should be able to sum moments here, or here, or here, or here, or here, or here. Any point in space, any point in the universe. If something is going to be in equilibrium, the forces in it must produce zero moment or balanced moments, no matter where you're summing moments about. That is one of the fundamental aspects or fundamental properties of equilibrium, of static equilibrium. Where you sum moments about does not matter. Now, some points are more convenient than others, and some points allow you to cancel moments out and things like that more easily, or have crucial forces that generate zero moments at certain points. But again, if something is to be in static equilibrium, and I do like keep pounding this home, you'll see me reference this in many of my lectures for this course. You've heard me mention it in many of the lectures and many of the videos, is that fundamentally, if something is going to be in equilibrium, it must be in rotational equilibrium about any point in space. So, and also about translational equilibrium about any set of chosen axes. So I'm choosing point E because, not because it's the only point we can sum moments about, but simply because it's a very convenient point. FDE and FEL both have lines of action passing through there. They will not generate moments there, which means the only unknown force that will generate a moment there is the force in member LM here. So first, I'm going to have HY here, that 5.625 kips. And that's going to be a negative moment because it's clockwise rotation about point L. So I need to put a negative on there. Negative 5.625 kips times a moment arm length of 48 feet. Then I need LM here. And again, this is about point, oh, actually, I have made a terrible mistake. It is not 48 feet. I need to consider this additional 12 feet. 48 feet is from H to L, so if I was doing moments about L, that would be correct. But I'm doing moments about point E, so I need to take into account the additional 12 feet of horizontal distance from point L to point M. So in fact, that is actually 60 feet. 60 feet rather than 48 feet. Sorry about that. Then I need to consider the moment generated by force LM about point E. And so I'm going to have, let's see, this is going to be a positive moment because it's counterclockwise rotation about point E. So plus FLM times a moment arm length of the vertical distance of 9 feet. And this is then all equal to 0. And so then FLM is going to be equal to 5.625 kips times 9 over, actually 60 over 9. 60 feet over 9 feet. And that will come to a value of, it's going to be tension, going to be positive. So 5.625 times 60 divided by 9. And that comes to 37.5 kips exactly. And this is going to be in tension. And this is one of our final answers we wanted. Oh, let me not, 325 there. Or actually 375. Let me put a proper box around this. And I'll put a proper box around this here. And that about finishes out this example. So again, we are just looking for a couple member forces, and that allowed us to get it very quickly. So, and that just demonstrates at a very basic level the method of sections for analyzing trusses. Now, another crucial element of this is think back to the method of joints and imagine how tricky it would be to analyze this problem using the truss method of joints. Say I wanted to get this section here, or this member force here. If I wanted to get the force in member EL using the method of joints, what would I have to do? Well, first of all, I would have to use a I'd have to use the same solving for external reactions as the first step. And then I think the easiest place to start would be over here. I'd have to apply a method of joints to get this to get the force in this member and this member. This would be a zero force member, so I could choose that one of it and say, oh, that's a 0. And this member force is the same as this one, and this is the same as this one. Then I'd have to use a method of joints to find the force in, probably at joint G here to find the force in member FG and GN. Then I have to use then I would have to use the summation of forces on joint N to find the force in member MN and FN. Then I have to do the same here to get this force and this force. And then I think finally at that point I would be able to use this member's joint equilibrium to get LM. Then I'd have to do one more joint equilibrium on this joint to get this force and this force. I guess we could just say that force. And really, that's it. So, but you can see how laborious that process would be. If I were to use a method of joints for this, it would be an incredibly long process. Now, it wouldn't be that difficult conceptually, and the math isn't that complex, but it is a fairly long and tedious process. We'd have to work through 1, 2, 3, 4, 5, 6 different joints, which means 12 sets of equilibrium. So yes, this would be a very tedious process to say the least. It could be done and it wouldn't be that difficult, again, in terms of just raw math. There's not even an integral in there at all or anything like that. Literally just, basic geometry and trigonometry. But again, it's very tedious to work through all of those joints. What we've been able to do instead with the method of sections is that when we're looking for this internal member force, we can just cut out an entire section of the truss, just an entire giant chunk of it, and look at what forces are in that member directly, which can be very useful. All right, so now let's look through a different example. And in this example, I want to work through a truss that is actually statically indeterminate, rather than the usual trusses that are statically determinate. So example 2, which will be a statically indeterminate truss. Now, we know, of course, that the very definition of static indeterminacy is that we cannot completely solve for all of the forces, reactions, etc. So we're never going to be able to completely solve this system, this truss that I'm going to draw. But that doesn't mean we can't still get useful information out of it. So let's say we have a truss like this, given. And we have a very, interesting truss to say the least. I'm not sure why you would build a truss like this, but let's just say you did. And we'll have a truss like this. It's kind of like a big right triangle. And I'm going to have this thing supported by 3 pin joints, or 3 pin supports. So we have 3 pin supports on, maybe there's a big vertical surface here, and we have these pin supports that this truss is going to be attached to. Like so. And let's say we have, some verticals here and here. We have a really complicated section over here with lots of different members, and then maybe something like this. Maybe something even, I think that's fine for now. Maybe a 0 force member there. And then maybe something like this. And I think that'll do it. Then let's go ahead and get the some dimensions on here. Let's say I did the last one in English units, so I'll go ahead and use metric for this. So let's say at the base here, this is 4 meters, 4 meters, and also 4 meters for some simple 3, 4, 5 triangles. And then for the vertical distances, let's say these are, I don't know, maybe, let's do it like this. Maybe this overall thing is, let's see, if I made these 3 and 3, I'm thinking of making these 3 high. So from here to here is 3 meters. And from here to here is 3 meters. And the same for the other joints. And from here to here is 3 meters. Not really demonstrating proper drafting technique here. 3 meters. And let's say these are just halfway up then. Maybe this is at oh, maybe this is, so if the overall height is 3 meters, maybe this is at 4.5 meters, and this is at 4.5 meters. And I think that would be enough to locate all of the, to give definite location to every member in this truss. Okay, then let's say we have a force applied of, I don't know, maybe 10 kilonewtons. And just for fun, let's say this thing is at an angle of 45 degrees. Then let's give some joint names. Maybe that in purple, A, B, C, D, E, F, and then G, H, I, and J. And all of these members are, of course, straight members connected by pin joints. So let's then say we want to know the force in some members. And let's say we want to know the force, find the force or the forces in members, let's say IJ, and let's do CI. And IJ and CI. So I'm going to go ahead and star those, or just mark them a little bit. Maybe in yellow here, just a little. We're looking for this one here. Oh, that's going to go away. A little star for IJ, and a little star for CI, because those are the member forces we're looking for. Now, the next thing we want to look at is, well, I would like to determine whether this is, or prove whether this is or is not statically indeterminate. So, if we remember from last time, or from lecture 9, when we were discussing truss theory, one of the core concepts, one of the core equations, was m plus r equals 2j. And that is if a truss is to be statically determinate. So let's look at this. M, let's count the number of members. 1, 2, you know what, I think I'll maybe count them by going around than counting the interiors. So 1, 2, 3, 4, 5, 6, 7, 8. Again, around 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 around the exterior, and then the interior members will have 1, 2, 3, 4, 5, 6, 7. So a total of 15. 8 around the exterior, and then 1, 2, 3, 4, 5, 6, 7. So 15 total. Then reactions. Okay, we have 3 pin joints, or 3 pin supports, I should say. And each of these is going to have an X and a Y reaction force, which means we'll have a total of 6 reactions. Next, we'll have joints, so A, B, C, D, etc. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 2 times 10, which means we have 21. Well, that's not equal to 20. That's greater than 20, so this is indeed a statically indeterminate truss. We are fundamentally incapable of solving for all of the forces in this truss, or at least for all of the reactions in this truss. Now, I shouldn't say we are fundamentally incapable. If you apply some basic principles of mechanics of material structural analysis, linear elastic analysis, that sort of thing, you can analyze the truss like this if you know what the cross sections are and what the material it's made of. But with statics, again, the nice thing about statics is that we don't have to worry about cross sections or what the thing is made of, and so we can't so easily. But that does make the analysis a lot cleaner. But unfortunately for this one, we some idiot, obviously me, put way too many supports on this thing, and now this thing is horribly statically indeterminate. And so we no longer have something that we can directly solve for all of the forces for. So does that mean we just have to give up and go home? Well, you might be tempted to, but the answer is actually no. I'm going to be able to solve this problem just because something is statically indeterminate doesn't mean we can't find anything. We won't be able to find everything, but we will still be able to solve for some things. And we're looking for this member force and this member force, and there's no reason we can't solve for those using the method of sections. So what I'm going to do is I'm going to start by saying, okay, we need to solve for some sort of or we need to select a section that'll have those member forces. So I know my section needs to include this and I know it needs to include this. I know that much at least. Then I also know that it's going to have I also know that it should cut out something relatively cleanly. And I don't really want to include all the left side of the truss because then I have to deal with all those reaction forces, etc. I think it's going to be really the only logical path for this is to use a cut that's like this. And I'm just going to cut out just this left side of the truss here. And that's going to let me solve for only those pieces that I'm interested in. So the only joints that are going to be included in this section are joint C and joint D. So notice I'm not even going to bother solving for the external reactions here. I know that I can't. If I try to treat this entire truss as a single rigid body and solve for those unknown forces, I'm going to have a very bad day. I'm going to have a very bad time. And the reason for that is that I have 6 unknowns and I only have 3 equations of equilibrium for a single rigid body. I am not going to be able to directly solve for all of those external reaction forces treating the truss as a single rigid body. So let's just go ahead and draw this out. So this is the cut section here. And the cut section, maybe I'll show some little stub members here, the members that I've cut. That's purely style choice and it's totally optional. Sometimes I do, sometimes I don't. But it's whatever you're in the mood for or feeling at the time. But at the very least on your free body diagram, you should show the forces. On your free body diagram, you do need to show your forces and the cut member forces, and of course any applied forces. So we have joints C here, and then D here, and then down here we're going to have joint I, and I should also include joint B in the diagram. I like to include any points that I'm going to have forces pointing towards, just in case I want to do some sort of balance of moments about those points later. That thing keeps wanting to pop up. Okay. So we have that. Now let's go ahead and show our forces. And I'm just going to go ahead and break this up, the 10 kilonewton force, into its x and y components. So I'm going to have 10 kilonewtons, or actually 10 kilonewtons times the sine or the cosine of 45 degrees, which of course is just root 2 over 2. So I have, let's see, that's going to be 10 root 2 over 2, which is just 5 root 2 kilonewtons in the horizontal direction, and 5 root 2 kilonewtons in the vertical direction. 5 root 2 kilonewtons in the horizontal direction, and 5 root 2 kilonewtons in the horizontal direction. Then I'm going to have FCI, the force in member CI. Again, notice I am assuming tension for all of this. And then FDI, the force in member DI. And then FBC, the force in member BC. Here. All right, so let's see. We're looking for well, let's see. Oh, actually, sorry, that should be. I think I have labeled that joint twice. I am not very smart. Okay. Oops. So I actually labeled. Now I'm looking back. That is actually a major issue. Sorry about that. I definitely seem to have labeled that joint twice. We have, I called it joint J here, so I guess I should just forget the D. Forget joint D, this is joint J. We'll just have some really weird names here. Sorry about that. Gotta be careful when going around and labeling joints. So we have FJI now. FJI, or actually FIJ if I'm going to be consistent. In member IJ and CI. So we're looking for this one and this one. All right, so let's see, how could we do this? Well, the easiest way to do this, well, actually, let me put the dimension here, a crucial dimension. This is 4 meters. And the easiest way to start with this is going to be, well, actually, this is a bit tricky. This is actually quite tricky. So I was tempted to do the sum of moments about joint J in order to get FBC, but the problem with that is that, well, actually think about, oh, actually that's not gonna be a problem at all. That's gonna work out just fine. If I do a sum of moments about joint J, something that is actually should be fairly apparent just by looking at it, even before we do the method of sections, CI is really a zero force member, is it not? So let's actually prove that. Let's do a summation of moments about joint J. I will have, well, let's see, FBC at the 5 kilonewton, 5 root 2 kilonewton, and this 5 root 2 kilonewton, or 5 root 2 kilonewton, and Fij, none of them will generate a moment about point J. So all I'll have is FCI. And that would be a negative moment. So negative FCI times a moment arm length of 4 meters, and then that just equals 0. So FCI must equal 0. It is actually a 0 force member. Oh, that's convenient. So that's actually just equal to 0. Then I can do a summation of forces in the vertical direction. And I would get, let's see, well, this is not going to generate any force. And I would have at negative Fij. And to get its component, well, realize this is a 3, 4, 5 triangle. 3, 4, 5. 3 in the vertical, 4 in the horizontal, and 5 in the diagonal. So I just need to multiply by 3, 4, 5, or 3 over 5 to get the vertical component. And then the other vertical force is the 5 root 2 kilonewtons. 5 root 2 kilonewtons. And this equals 0. And so Fij then is going to be equal to 5 times 5 root 2 divided by 3 kilonewtons. If I mathed that correctly, that does sound good. That does seem right. So 10 root 2 over 3 kilonewtons, and that would be our final answer. And really, that's it. So notice, using this method, we don't actually have to even have a truss that is completely statically determinate. I have a problem here that because I'm not interested in every force in every member in the truss, I don't need to worry about, oh yes, it's definitely extremely statically indeterminate on this end. If all I'm looking for is the forces in these members over here, I can just cut out that section and only that section and say, I don't really care what's going on the left side of the truss here. As long as this equation is going to be in equilibrium, as long as we still believe in the laws of Newton and the laws of statics, if this thing is going to be in equilibrium, any piece of it we cut out must be in equilibrium as well. And that truly is the core principle of the method of sections. If an object is going to be in equilibrium, every single piece of that object, no matter how small, is going to also have to be in equilibrium. And that is, I think, there's a reason I like using this example, because it really does demonstrate that you can take a piece out of a section, and you can take a piece out of a truss, or any rigid body, and if that whole thing is going to be in equilibrium, then every piece of it must also be in equilibrium. And we'll be applying this later when we look at frames and simple machines and shear and bending moment diagrams and other related topics. All right, that'll do it for now. Thank you for watching. I think this will be the last portion of Lecture 10. Please let me know if you have any questions. In Lecture 11, we will be moving on to looking at frames and simple machines. All right, hope you've all learned a few things here. Hope you've all enjoyed this. Please let me know if you have any questions. If not, I'll see you soon for Lecture 11. And as always, thank you.